one more of these tests. This is the second derivative test for local extrema. Okay? So think about it for a moment. If I have, let's say, any kind of graph, right? Okay. And I can see that I have a place where there is a horizontal tangent. Okay, so you see I have a horizontal tangent here and a horizontal tangent here. If I have a horizontal tangent and it's concave down, what are we going to have? A maximum. And here, if I have a horizontal tangent and it's concave up, I'm going to have a minimum. Okay. Now remember, when we do concavity, what are we looking for? Not the first derivative, but second derivative. So here's an example. So f prime of c equals 0. Okay, that means there's a horizontal tangent. And if I know the second derivative is less than 0, then it's going to have a maximum. So here's my example. F of x equals negative x squared. We know what that looks like. But let's just go through. We know f prime of x is negative 2x. Right? So that means there's a critical point at x equals 0. So if I can figure out if it's concave up or down at x equals 0, then I can determine that it's a maximum or a minimum. Yeah, well, I thought that it's second derivative. Right, so first thing we're doing is this part. Okay, so we're basically saying figure out where there's a horizontal tangent. By the way, this is not for corners or cusps. This is only for horizontal tangents. So now if I go from here, go here, and find the second derivative, what's that going to be? Negative 2, which is less than 0. Therefore, there's a local maximum at x equals 0. I mean, this is a very simple one, but when you have more complicated ones, if you find out there's a horizontal tangent and then you do the second derivative, there's nothing to plug in here necessarily, but let's say it was negative 2, x plus 1 or something like that, you would plug the value in. This, you would plug in 0. So I didn't have to do it here, because if I plug in 0, it's constant, it's just negative 2. But sometimes we do have to plug in, and sometimes we just have values like I have below. So now what if we have a horizontal tangent, but this time the second derivative is greater than 0. So it's concave up, we have a minimum value. So if we do f prime, we get 2x. Obviously our critical point is at x equals 0. When we do the second derivative, we get a positive value. Therefore, local minimum. And actually, these are also absolute maximums, but the test is just for local. Okay, good? Makes sense? All right, let's take a look. We have a continuous function from negative 1 to 6. We have f of 2 equals 5, f of 5 is 0, f prime of 2 equals 0, f prime of 5 equals 6. Second derivative at 2 is negative 3. Second derivative at 5 is 0. Okay. All right, so using the second derivative test, what do we first want to look for? We want to see where the first derivative is equal to 0. Do we see any first derivatives equal to 0? Okay, so this part, f prime of 2 equals 0, tells us there's a horizontal tangent at x equals 2. Okay, so first, if we're given a list of values, we look for the one that, and that's the only place where we had a first derivative equal to 0, right? Okay, now what do we want to consider? The second derivative at that same x value, which is -3. Which implies this is concave down. Good. So if we know we have a horizontal tangent at 2 and it's concave down, what do we have? Maximum. And what is our maximum? So in a situation like this, we had additional information that was completely unnecessary. So kind of like when we did the inverse functions, right? We didn't use this, we didn't use this, we didn't use this.
It's wrong to say the maximum tax equals 2.
Well, you could say, it says find the local extrema, which means technically we're looking for the y value. If I just said where it is, then you would say it's located at x equals 2. Does that make sense? Questions? Okay. Let's do another one, but this time we'll do a table. Okay, what's the first thing we're looking for? We're looking for where the derivative is equal to 0. Yep. Okay, f prime of 1 equals 0. This implies there's a horizontal tangent at x equals 1. You kind of see the steps, so we look for one thing. Now what do we want to look for? We want to see the double prime at 1. F double prime of 1 is -1. So this tells us it is concave down. So this is going to be the same idea. This one's going to have a maximum. Let's see. What is our maximum? F of 1 is -6. Good. All right, last example. Okay, I gave you a first derivative. F prime of x is 4x cubed minus 12x squared. We want to identify where the extrema of f occur. We want to find intervals of increase, decrease, concave up, concave down. And then last, we're going to sketch a possible graph for the original function. Okay? All right. Good? Okay. Notice this says where. Anytime it just says where, that means it's only going to be x values. I don't have the original function, so I'm unable to find the actual y values. I'm just finding that. Well, I already gave you the first derivative. Just set it equal to 0. So let's take, so for part A, take f prime. Before I set it equal to 0, let me just factor out a GCF. What can we take out? Or x squared, and we're left with x minus 3. Where do we have critical points? 0 and 3. Okay. Let's make a number line. What's that? So I didn't have to do, basically everything we've done so far is just the algebra because I already gave you the first derivative. If I gave you the original function, we'd have to do the derivative and set it equal to 0. Okay, 0 and 3. What do we have on our number line? If we pick something less than 0, it's going to be negative. If we pick something between 0 and 3, still negative, and then, which makes sense, because if we look at the multiplicity at 0, it's 2, so we know it should not change signs. Okay, so it's going to increase continue to increase, decrease. So it says identify where, I'm sorry, I got that completely backwards. Thanks. Okay. Decrease, decrease, increase. There we go. So we just have a minimum at x equals 3.
See why they are doing that.
Because we don't know f of x. So when we get to the next chapter, when we start working backwards and doing integrals, we can't figure out what f of x is. I mean, we can find out what a general look for f of x, but we can't find the actual y values. And the reason being, what happens when we do the derivative of a constant? It disappears. It becomes 0. So if I were working backwards, do we know where the graph is? There could be a vertical shift. So this just tells us about the slope. We get a general idea of the graph of the original, but we don't know its actual location. Does that make sense? Yeah, that's where the plus C, if you have heard of the plus C dilemma, that's where that comes in. Okay, B, we already did all the work for it. So where is it increasing? So F increases where? 3 to infinity. And F decreases from negative infinity to 3. You don't need to put 0 as a point and put there. You don't need to do that. If it decreases and continues to decrease, we just go straight from negative infinity to 3.
In the brackets and parentheses.
It doesn't matter here because these aren't endpoints. Okay, now we want to do concavity. So let's do, we have the first derivative, what we started with. We'll do the second derivative. So what's that going to be?
So
12x squared minus 24x. Good. I'll factor it. We'll take a 12x and set it equal to 0. So we get 0 and 2. All right. Now, so I'm going to make another number line. But this number line is going to be f double prime. Okay, what do we have? So this will be negative times negative. So it'll be plus minus plus. Sound good? So it's concave up, concave down, concave up.
So do the brackets matter? Like, when do you know when it's fine to do brackets? Like here, we're not including.
because concave you only use parentheses.
Concave, we only use parentheses. And increasing and decreasing, you can use parentheses as long as it's not an endpoint of a function. Like if you have a closed interval, you must include the endpoints. Okay. All right, last one. Okay, so what I'm going to do is I'm just going to make an x-axis. Okay, because my y-axis is not important here at all. Because remember what I said? I don't know what my y values on my original graph. But I do know what's happening at 0, 3, 0, and 2. So what I'm going to do, I'm going to place the numbers where the concavity changed, and I'm going to place where there were maximums and minimums. So I'm going to put 0, 2, 3. Okay. Here's the tricky part. How are we going to put this all together? Okay, so what's happening first? It is decreasing until we get to 3. But it's also concave up until we get to 0, and then it changes to concave down. Okay? Then it hits a minimum, and it's concave up. What do you think that's going to look like? No idea? Okay, well, what's decreasing and concave up? All right, it's almost easier to kind of, let's just forget the x values for the moment. Let's just think about what that looks like. So here, I'll do it on here since I'm screencasting. So it's going to decrease and it's going to be concave up. So it's going to be like half a smile, right? It's decreasing, concave up. I'll move it over here in a minute. Just wanted to make sure you understood that part. Then what happens?
Then
It continues to decrease, but it becomes concave down. So it's going to flip like that. Then it's going to become concave up and hit a minimum and then continue. So it's concave up, concave down, continuing to increase, switches to concave it up, hits a minimum at 3, and then increases. Okay, so now where do we want to place this over here? Or maybe we could just put our number, maybe I'll just move my number line over. And what values do I want to put here? What's happening right here? So that's going to be x equals 0. Okay. Then what happens here? Switches to concave. So it's like, these are my critical, well, not critical points, but this is 2 and this is 3.